And this is for you pick one for your test. No hurry, no hurry. And I think there may be one or two other people who I need to give this to. So, yeah, that's for the test. See, everyone, none of my Abbeys are here. Okay. Looks like some of you are all ready. Don't rush if you're still enjoying the process. But if you want to hand yours in, or is this okay? Okay. Then I could take what you have and we'll see how things go. You're all set. All right. I don't want to rush you guys. Good job. Very nice. Beautiful. Good job. Very nice. This here. Take your time. I'll come back. Wow. Very nice. Good job. I'm not rushing you, am I? Okay, good. Perfect timing then, yeah, because I gave you yours. You were the last person to get it. So you deserve another minute at least. Okay. That's good. That's good. That's good. Is this it or is this old? No, this is it. Okay, I see you're doing a secret note. That's okay. You keep going. What else? I know, I know. Well, you'll just have to do well on the next test as well so that you can get another one. Oh, you're all set? Okay. I should have asked before I stapled. Do I have them all? Whew, good thing. All right, let's take a look and see what we have. Um, so first things first, I was, I guess, kind and didn't make you write this out, but you'll write it out maybe next time. Maybe I'll put that on Monday's quiz, is to write out that list just so that you can do it yourself. But you can count those. There's 8 of them. A is the event of 2 heads. Exactly. Because as Oz probably figured out, if you said just at least 2 heads, it's a different number. But exactly 2 heads, there's 3 of them. If you interpreted that as being at least 2 heads, you would have gotten 4. And I guess I should accept that, even if, since even though I mentioned that in front of everyone. And then this is, of course, 3/8, very nice. And then here you just have to figure out how many black cards there are, the wilds. Basically, if you're familiar with Uno, if not, you could probably figure it out anyway. So 24, 24, 24, and 24, add those up, you get 96. 108 minus 96 is 12, so there are 12 black cards out of 108. And that's it. Good job. I hope everyone got 100. It's always fun to just go through and just be 100, 100, 100, 100. Yes, sir. Two exact, no, just 2 heads. So here's an example. These are 2 heads. These are 2 heads, and these. So there has exactly 2 heads. So if you interpreted it, if you got 4 out of 8, I would probably just say, I'll do this. How about if you got 4 there, I'll do this, but I won't mark it wrong. So, all right. Anything else? Other complaints, concerns? Oh, you have 2 out of 8. Okay. If you have 2 out of 8, I'll do this. How's that? Just so you know. Okay, let's move on though. So we have more probabilities today, and in particular, we're going to do some gambling. But don't worry. I'm gonna be, I'll let you know where I stand on gambling. I think it'll be okay. But before we do the gambling, I need to mention a couple of things about the way that we talk about probability. And this is going to bother me if I don't fix it. Just a minute. Full screen mode. There it is. Oh, so are you done with the stickers? Yes, you are. Did anyone else not get a chance to get a sticker because you did so well in the test? And by so well, I don't, you might have only gotten a 70 and thought, I didn't fail. Yeah, so anyway, you can come up afterwards if you need one. Uh, I forgot to bring them on Wednesday. Okay, so more probability. So some terms that we're going to deal with. Discrete. You know what the word discrete means. It means that there's separations between the different outcomes, like the number of coins, number of heads when you flip 3 coins. That's a good example of discrete probability. So a discrete random variable is just a random variable. I know all these words. You don't need to, yeah, these are words that I use. You're not going to use them generally, but I'm stuck using them. So anyway, discrete random variable are just variables whose possible values are a list of distinct values. Like when you flip 3 coins, you either get 0, 1, 2, or 3 heads. 0, 1, 2, 3 heads. A probability density function, technically, I'm using the language that our book uses. It hurts me a little bit to use this language in this setting, but I'm going to use it anyway. Probability density function is just a list of all the probabilities. That's all. Just a list of the probabilities. I would have called it a probability mass function. Now I've got it out of my system. Okay, so a couple of things to note is all probabilities are going to be between 0 and 1. And then the sum of all the probabilities is 1. So just as an example, let's take that coin flipping thing. Let's just go back. I was going to write it up here on this blank slide, but let's just go back to the quiz, which I know you don't have in front of you. It's up here, but I have it. So here are the outcomes in the quiz. So at least according to our book, they would call this a probability density function. I would call it a probability mass function. So x and then the probability of x. So let's say I want to know the probability of 0 heads. I could do that by using this sample space up here. Just go up there and figure out how many times are there 0 heads and just write it as a fraction. Well, what are the other possibilities? You could have 1 head, or you could have 2 heads, or you could have 3 heads. So I've got this table, and on that table I list off all the different outcomes. And of course, because I'm a mathematician, I use a letter, but you could just write down number of heads, and it would mean the same thing. And then down below, I'm going to put probabilities. I'm so confident that you guys can do this that I'm just going to pick people out of the blue, like Carson. Carson, what is the probability of no heads? Yeah, 1/8. Very nice, because there's exactly one way that you can have no heads out of 8 total. Next one, Will, what about 1 head? 2, which let me go ahead and highlight them for you. 1 head, you saw this one, right? And then let's see, this one. And then what about this one? Okay, thank you, Will. I appreciate your good naturedness about it. So what was it again? 3. Okay, yeah, 3/8. Very nice. So it's 3 out of 8 for 1 head. Yeah, it's early. It's early, and you're still. Is that water or is it caffeine? Oh yeah, it's not going to help you. Well, it will help you do something, but yeah. Okay, you're not here, so you can't help, but Ethan is. Ethan, what about 2/8? Oh, we did this one already, but what is the probability? Oh yeah, sorry. 3 out of 8, 2 heads. See, I need my caffeine as well, apparently. I only had 1 coffee this morning. Okay, one more, and that's the last one. And actually, no, let's not ask anyone this one. I want to point something out about a probability distribution like this, and that is that the rule is that the sum of all the probabilities is equal to 1. If you think about it, if you take anything that could possibly happen, you're going to get 100% of the outcomes. And so when we look at this, we could actually count the number of times that you could have 3 heads, and I know you already see it, don't you? You see it. Or I could say, okay, I've got 1/8, 3/8, 3/8. I need the total to be 8/8. And so I've got 7/8. That leaves 1/8 to go here. So that's how that's going to work. So that's an example of a probability distribution, or what they call a probability density function. Kind of rankles me to say it that way. I'm going to move this down here so I can use it a little later on. There it is. This is 3 coins, or flip 3 coins. X is the number of heads, just so I can remember what I've done. Okay, let's go back to PowerPoint land. So on your homework, you're going to have things like this, where you have to figure out the missing number. Take a minute, see if you can work out the missing number in that probability distribution or probability density function, if you want to use that language. So it's not too hard, but I'll give you a minute. All right, Avery, I know you know the answer, don't you? It is 4. How did you get 4? Yeah, you just add them up, you get 12 out of 16, and you're like, well, 12 out of 16, I need another 4 out of 16 to make this add up to 1. Very nice, 4 out of 16. By the way, this is actually the probability distribution for flipping 4 coins or having 4 kids. So the probability of having no heads, 1 head, 2 heads, 3 heads, and 4 heads. So anyway, moving on. Let's see, what is this? Do I want to do that? Yeah, why not? So once you have this probability distribution, what you could do is you could answer questions like, what is the probability of having a 1? So I don't know what these represent, but whatever they represent, I could say the probability of having a 1 is 0.11. I could answer the question, what's the probability of having a 1 or a 4? So notice a 1 or a 4 means either of those. And so there's this much of a chance of having a 1, this much of a chance of having a 4, and you could just add those together. And you'll get the probability of having either of those happen. So this would be 0.52. This would be akin to me going back and asking, what's the probability of having either 2 or 3 heads? 2 or 3 heads, you remember that one? So the 2 heads was 3 out of 8. The 3 heads was 1 out of 8. Add them together and you get 4 out of 8 to get 2 or 3 heads. Now this one, you might say you can't answer that, but you actually can. What's the probability of getting a 3? It would be the same as if back here I'd asked, what's the probability when I flip 3 coins? What's the probability that I get 4 heads? It's 0. It's impossible. And so, any number that's not on this list, since I've got every possible answer on the list, any other number like 4 is going to be a 0 probability. So don't be scared if you see something like that, where it's asking you for a probability that doesn't exist in your table. It just means that there's no way that it could happen. There's a 0 chance of that happening. All right, so one more thing, and then we get to start moving into gambling. And that's this. I want to know which of these are valid probability distributions or density functions, whatever you want to call them. So take a look at these and see if you can explain whether yes or no, which one is correct, which one is real, which one is not a probability distribution or density function. So take a minute, you can look those over, talk to your friends if you need to. And I guess I should finish taking attendance while you're doing that. Oh, I did take attendance, never mind. Oh, I guess I should maybe, just in case, because some of you are thinking, what? Okay, here's the deal. Valid means that it works, it's real. It means it fits these 2 bullet points here. So those 2, all the probabilities are between 0 and 1, and the sum of the probabilities is equal to 1. So if you were confused about what I meant by valid, that's what I mean. So I'll give you another minute, and then I'll start picking random people. All right, Sarah, do you want to talk about any of these 4? Yeah, or invalid. Either way. Oh, wow. Second and the 4th? Wow, okay. So let's see, that's this one, and this one you say are valid. Now, why would you say that they're valid? All right, yeah, that's a good reason. If they add up to one and they're all the numbers are between 0 and 1, then you're good. So Sarah apparently added up all of these numbers and got 1, and added up all of these numbers. These are a little easier to add up. You have 0.3, 0.3, that's 0.6, 0.7, then 0.9. Yeah, 1. Now, that one's a little harder, but yeah, you do get 1. So both of those are good. So apparently Sarah thinks the other two are not good. So let's see about if I've already picked on you. Let me take someone else. So Karen, one of these other two, apparently Sarah doesn't like them. Do you like either of them, or what's wrong with pick one? This. Oh, a negative. Yeah, you can't have negative probabilities. Probabilities are never negative, and probabilities are never greater than 1. This is why mathematicians always make fun of your coaches when they say, give me 110%. Makes no sense. 100% is the biggest you can go. I know what they mean when they say this, but I still make fun of them. But anyway, so yeah, this does add up to 1, by the way, if you do the negative and the positives. But no, it's bad. No, because of this. All right, let's find one more volunteer. So Elizabeth, what do you think of this first one? Apparently Sarah doesn't like it. Do you like it? You have a suspicion, a sneaking suspicion that they probably don't add up to 1. Let's check. Let's check. Um, so let's see. We've got, oh, 1.1. Is that what we're getting? Anyone else do this? Yeah, okay. So yeah, this one actually, it's you can add it up pretty quickly because 1 plus 2 plus 3 plus 4 is 10. So all of that will be 1.0. And then 1 plus 2 plus 3 plus 4 is 10 as well, but it's over here. So that's why that's there. Nice. So this one's no good as well. No. All right, very nice. So you got your homework, at least part of it will be like this, part of it will be like this, and then the last part will be the gambling. That's the most, well, most interesting. So what I've done is I've invented some gambling games, and actually, I'm actually going to go, so they're all about John and Jim. I'm actually visiting Jim this weekend. He was in the hospital this past week because his foot, I don't know, he had like a metal spike put into his, no, like he showed me the x-ray. It's like this, you don't know Jim, never mind. But anyway, so I'm going to go visit him tomorrow to see how he's doing. But that he's the Jim in this particular story. So maybe I can get him to do some of these gambling games with me when I'm visiting him. But so what I'd like to know from you is which of these games are fair. So I think you probably have a sense of what it means to be fair. And so if you set aside for a minute the idea that gambling is wrong, I'll explain why I think it's wrong in a bit, but um, let's just examine these because they're nice sort of tools to understand this next concept, is what we're doing here. So let's take a look at this. Jim and John flip an unbiased coin. And if the outcome is heads, Jim gives John $1. And if the outcome is tails, John gives Jim $1. Sounds fair to me. What do you think? Is that a fair game? Does anyone want to, I don't want to randomize because I don't want to pull someone out, but does anyone want to explain why you think it's fair if it is, or why you think it's unfair? Okay, Hayden, figured you'd want to jump in here. Okay, so you got like a same chance of winning as losing. There's a balance there. Yeah, I was trying to indicate that. Very good. So 50-50, that's very good. So so the fairness has to do with we have the same chance of winning. So I thought I'd play a different game with Jim. And you might think I didn't change anything, but you'll notice one thing changed. So in this case, Jim and John flip an unbiased coin, and if the outcome is heads, Jim gives John $2, and if the outcome is tails, John gives Jim $1. Sounds fair to me. We each have 50-50 chance of winning, right? 50-50. So what's wrong with that? Wait, wait, who said that? Okay, what do you mean by consolation prize? Okay, so there's an imbalance in the payout. Okay, so not only do I have to balance the probabilities 50-50, but I have to balance the payout. Otherwise, I'm going to win half the time. Jim's going to win half the time, but I'm winning more money than Jim. So over the long haul, I'm probably going to come out ahead. Okay, well, let me try to balance the payouts. So how about this one? I've got a die, a six-sided die. You know what these look like? Numbers 1 through 6. And if the outcome is either 1 or 2, John will give Jim $1. Isn't that magnanimous of me? Otherwise, Jim gives John $1. The payouts are balanced here. Doesn't that seem good? Okay, what do you think, Caleb? Okay, so now you're complaining about the probabilities again. So now I'm going to be paying Jim only a third of the time. Jim will pay me 2/3 of the time. Okay, well, let's see if I can get things a little bit better. What about this one? Jim rolls one six-sided die and John rolls one six-sided die. If the two dice match, John gives Jim $4. If the outcome of Jim's die is less than the outcome of John's die, John gives Jim $1. Otherwise, Jim gives John $3. I know, this is kind of like what people like the casinos do to you and the lottery commission is they come up with something that is complicated enough that you're like, wait a minute, is there an advantage one way or the other? And it's hard to tell. And so this one, maybe we should table this one until we can put some math behind it, which is what we're going to do in just a minute. And just one more, and this is like a particular casino game. You have that Jim plays with John. 70% of the time Jim loses $1. 20% of the time Jim wins $1. 9% of the time Jim wins $2, and 1% of the time Jim wins $15. This is actually based on a casino game called Keno, where it looks like the lottery with balls coming up and whatever. But I've never been to a casino. But anyway, yeah. So it's hard to tell who has the advantage. We're going to be able to tell in a minute. Before we do that, though, here we go. Let's talk about gambling. So gambling in the Bible, just briefly, just so I can get this off my chest. The words gamble, gambling, gambler, they aren't found, at least in the NIV of the Bible. I know that the soldiers rolled dice for Jesus' garments. But in Isaiah 10, we're told this: woe to those who make unjust laws, to those who issue oppressive decrees, to deprive the poor of their rights, and to withhold justice from the oppressed of my people, making widows their prey and robbing the fatherless. What will you do on the day of reckoning when disaster comes from afar? To whom will you run for help? Where will you leave your riches? Nothing will remain but to cringe among the captives or fall among the slain. Yet for all of this, his anger is not turned away. His hand is still upraised. This makes me fear for our country and our state, because we have made unjust laws that deprive the poor of their rights and withhold justice from the oppressed of our people. In particular, when we legalize gambling, it has been shown that gambling affects the poor far more than it affects the rich. So when we have like, who plays the lottery? It's the poor who play the lottery much more than the rich. I mean, the rich person might play a bit, but compared to their income, like if I bought a lottery ticket every day, it would be a drop in the bucket compared to someone who is on welfare buying lottery tickets. So back in the early 2000s, actually in the 1990s, Ohio rejected gambling. We did again in the early 2000s, like the late 2000s, like 2009. Finally, it just took one time for the idiots to get it to pass, and now we have gambling in Ohio, and it's just a tragedy. At least we've always had the lottery, at least since the 1970s. But that's my take on gambling. So I'm opposed to gambling. However, as you're going to find out, I do engage in some gambling, but not this kind. Okay, so expected value. This is the tool that we're going to use to, the tool we're going to use to evaluate those questions. Is this game fair? Who has the advantage? It's actually quite simple. I know that looks scary, but I think you probably already know what this big sigma means. The big sigma means add them up. So let me write this down in a more English. So here's what I would write down is Actually, what I would write down is the next slide. So I'll just show you this just briefly for those who love the symbols. We're adding something up. What we're adding up is we're adding up outcomes times probabilities. So here's a better way of looking at this. So if you really want to write that down, go watch the video and pause it. But here's the easier way. Number one, make a table describing the probability distribution you're interested in. We've already done that for a couple, at least one of our things today. Then the second thing, multiply each outcome by its probability. And then the third thing is to add up the results. And that's it. That's it. Once you have that, that's your average, your expected value. So expected value is an average. So let me write that down. That is important. Expected value is an average over time. Or, well, like if you were to play the lottery over and over and over again, I remember when I was in Philadelphia talking to a guy, he's like, yeah, I can't do a Philly accent, but I play the lottery, I play it every day. Sometimes I win, sometimes I lose. It all balances out. And I think to myself, yes, it does. It all balances out in the state's favor and not in your favor, that's for sure. Anyway, it's the average over time or over a whole bunch, like if you flip a coin thousands of times or whatever it is. So let's actually do this with this particular example. So step one, make a table. We've made a table. What is the average number of heads when you flip 3 coins? Well, let's make our table. Step two, we're going to multiply. So the product, I'll just write it down like this. X times P is going to be 0. And then this is 3/8. And then this is 6/8. And if you want to do this on your calculator, that's totally fine. I don't care. And then this is 3/8. I'm not going to bother with the 4. Usually we're just going to focus on the outcomes that are possible. Okay, now we've got that. We've made the products. Now just add them up. I'm going to actually make a second line here just to impress on you that this is a separate thing that you're doing. Add these up, and we get 12/8, which is the same as 2.5. Whoa, no, 1.5. Yeah, that's right. Okay, 1.5. And that's the expected value. So expected value, that's the symbolism. All it means is if we did this over and over again, what's the average? On average, if you flip a coin, like let's say all of us flipped 3 coins and we kept track. In fact, we're going to actually do this. I think it's not going to be until after spring break, but we'll do it with dice. Every one of us is going to roll a 6-sided die 30 times. There's going to be such a cacophony in here. I'm going to have to bring earplugs. But when we get done, we're going to average all of ours together and see what happens. So this is what would happen if we all flipped a coin 3 times. The average of all of our numbers would be about 1.5. Okay, getting back to the gambling games that we were doing earlier. Oh, come on. Sorry. There it is. So let's go ahead and take a look at this one. So this is the one, yes, Hayden. Same thing, yeah. Rolling 1 die 30 times is the same as rolling 30 dice 1 time. Yes. Yes, if you want to. Whatever. I'm going to bring about 100 dice with me, so I'm going to have enough for everybody. So if you want to pick out a few of mine too, that would be fine. Okay. Anyway, let's get back to this. Yeah, same thing with coins. If you flip a coin 3 times, it's the same as flipping 3 coins once. So you get the same distribution. All right, so someone said, I forget who, said that this is going to be fair. So let's get our probabilities. Let's see. And you always have to focus on like what's going on in terms of someone's wallet. So let's deal with Jim. Jim is giving John $1. That's a loss of $1. or Jim gives John $1. So those are the two outcomes. I need my probabilities, but I think you know what they are. Let's just find a volunteer. Sienna, what's the chances that Jim gives John $1? Yeah, it's a 1 out of 2 chance, right? I mean, this is what, I don't remember who said it, but they said, hey, it's the same chance, right? 50-50. Okay, very good. So we've got that. Now we're going to set up our multiply. So multiply these together, and I get -1/2. So this is going to be x times p. And this one is +1/2. So far, so good? We're just multiplying 1 times 1/2. And now the expected value is going to be -1/2 plus +1/2, which is 0. So mathematicians would call this a fair game because on average, it comes out even. That doesn't mean that at the end of the day, we both, John and Jim, both have the same amount of money. It just means that on average, we should have pretty close to the same amount. I might come out a little ahead, Jim might come out a little ahead, but on average, it should be about the same. All right, let's take a look at the next one. The next one, someone accused me of being unfair. Let's find out why. Oh, actually, we're skipping. This is the third one, but still. So we have a 6-sided die. We have similar situation where the outcomes in terms of Jim could lose $1 or Jim could gain $1. And I need to know the probabilities of each of these. So let's see if we can work this out. It's not too hard. So I'll find a volunteer here. So Trinity, do you know the probability that either one of these? I don't care which one. So, well, here's it's either a 1 or a 2 on a 6-sided die. How many things are on a 6-sided die? 6, and so there's 2 chances out of 1 out of 3. Yeah, so 2 out of 6 or 1 out of 3. And so let's just make sure we put it in the right place. There's a 2 out of 6 chance that John gives Jim $1, and since this is Jim's wallet that we're concerned about, I guess this goes right here, 2 out of 6. Very nice. All right, the other one is probably pretty easy, but let's make sure. So find another volunteer. August, do you know the probability that Jim is going to lose $1? Yeah, it's the otherwise because you have 2 out of 6, so 4 out of 6. Very nice. So you got a 4 out of 6 chance. Now we just have to go ahead and multiply. So I'm going to multiply things together down here, x times p. And so x times p here is -4/6. And like I said, I don't mind you using your calculator. Just if you do, don't round to like 1 digit. Use at least 3 or 4 digits if you would. So this would be -0.667 or 6667. Don't just give me 0.7 if that'll make me feel bad. And then this one is 0.333, but I'm going to write it as 2/6. Okay, so there's those. And then the final step is add them up. So the expected value is going to be -4/6 plus 2/6, which is -1/3. And that equals -0.33. Now let me point something out because this is going to bother some of you. The expected value is not one of those outcomes. The expected value is the average over time. So if we played this, if I got Jim tomorrow to do this with me, be like, hey, I got this die here. You want to play some gambling games? Anyway, at the end of the day, on average, Jim would lose about 33 cents for each time we played. So if we played 100 times, I would expect to be $33 ahead, and Jim would lose $33. So that's what that means. It means if we do this over and over again, on average, that's how much you should expect. That's why we call it expected value, how much Jim should expect to lose. All right, we got 2 more of these, I think. Just a minute, and then we get to, oh yeah, this one, maybe just 1 more. This one is kind of cool. Okay, so Jim rolls a one-sided, six-sided die, and John rolls one six-sided die. If the two die match, John gives Jim $4. Just a minute. I can't do this there's not enough room down there. I'm gonna have to put this onto Notability. Give me a sec. Let's see, done, copy and delete. Hold on a minute. Put this over here. Let's just plop this in right there. There, that's nice. Okay. Let's see if we can first of all identify the different outcomes. In terms of Jim, remember, we're always worried about Jim. I think you probably can tell that John in these scenarios is always going to, be the schemer and try to pull one over on Jim. So we feel that he just had surgery, Anyway, so you have X and you've got the probability. So let's see, what could happen? John could give Jim $4. So in terms of Jim's wallet, that's pretty good. John gives Jim $4. That's a net gain. Okay, what else could happen? Let's see. John gives Jim $1. Look at this. John's giving Jim tons of money. Otherwise, okay, this last one is losing $3. Now, the confusing thing here, I think, is trying to sort out exactly what each of these means. So to help you out, I have produced, or I've got here, I made a table of all the different die rolls. And so if you want to think of the white die as being Jim's die and the black die as being John's die, then we can sort out exactly what the probabilities are. First off, note that there are 36 different outcomes when you roll two dice. I'm going to paste that image in right here. Let's see. Let's paste it right there, I guess. Okay, I'll put it down there. We'll be able to go back and forth. Okay, so for example, it could be that Jim rolls a 1 and John rolls a 1. Or Jim rolls a 1 and John rolls a 2. Jim rolls a 2 and John rolls a 1. You see, these are all the possibilities. There are 36. So our job now, by the way, that's the sample space. That's all the possibilities. Now our job is to sort out what each of these things means. So let's do this one at a time. If the two dice match, that's the first probability. That's when John gives Jim $4. The two dice match. So let's go down here and identify how many times. Go ahead and count them up. See if you can figure it out. All right, Hayden, you got randomized. How many times? There are 6. Now, if you can't see them all, I'll highlight them. It's 1, 2, 3, 4, 5, 6. Those are the 6 times that the two dice match. And so the probability of getting $4, is 6 out of 36. All right, let's see about the next one. So the next one is if the outcome on Jim's die is less than the outcome of John's die. I want to know how many ways that can happen. So Jim is less than John. So let's go down here. And Jim is the white die, John is the black die. How many ways is Jim less than John? This one's going to take a little bit more thinking, but I think we can do it relatively quickly. So I'll give you a minute, though. And then just to warn you, Will, you're the one that got randomly chosen. So you know how many? Oh, yeah. You're Will, aren't you? Come on, man. How many ways can Jim be less than John? So you're counting up the number of ways that the white die is less than the black die. Go ahead and do that, and I'll pick another person to count the ways that John is bigger or less than Jim the other way. So just a minute. Dante, you get to count the other way. So just to be clear, Will is going to figure out the number of ways that the white die is less than the black die. Dante is going to figure out the number of ways that the white die is bigger than the black die. Just let me know when you got it all counted. Did you say 15? Very good. Yeah, let me highlight them all, and then we'll get to Dante. Don't worry. It's all of these, isn't it? all of these up here, because of the way I've arranged these, it's pretty easy to count. So you get 15. So very nice, 15. So there's a 15 out of 36 chance that that'll happen. And then Dante, did you count this other one?
Yeah.
15 as well. Yeah, it's the same because it's these 15 down here where the white is bigger. Yeah, so normally you're not going to have to go to these lengths, but I think this one's interesting enough that I wanted to do it. So now we've got that. Your next job is to multiply outcome times probability. So let's see if we can do that. We have 4 times 6 36ths, and then 1 times 15 36ths, and then -3 times 15 36ths. So take a minute, multiply all that out, and then the final step is to do the expected value, which is the sum. Once you have these numbers, you add them up, and that is going to be your answer. I'll give you a minute to do that. All right, does anyone want to show off what you got? Or just not show off? You got something? Okay, very good. -6 over 36 is what I got as well. 6 over 36. And that's 1/6. So it's approximately -0.1667. So what this means is that on average, it's negative. And so we're concerned with Jim, aren't we? Jim is losing 16 or 17 cents every time he plays this with me. So I will let him know tomorrow that you guys recommend he stay away from this particular game. Okay, let's see, go back here. All right. Okay, let's talk about the lottery. The lottery. So here is the lottery, the pick 3, but this is true of all Ohio State lottery games. So the scratch-off tickets, you can actually look at, go online and, well, not on campus because they've blocked the Ohio State lottery, which irritates me because I think it's something that we should be able to look at to get our probabilities for. But if you look at the scratch-off tickets as well as the big games, whatever, pick 3 is easy because you pick 3 numbers, and if your 3 numbers, you pay $1. You choose 3 digits, duplicates are acceptable. If your 3 digits match the 3 digits that are chosen at the end of the day, then you win $500. This is a typical way that the state rips off the poor among us because you have people who are like, oh, I just got to wait till I win. I'm going to win this time. But anyway, so we just need to know what are the chances of this happening. So in reality, if you win, you're not winning $500. You're actually winning $499. That's really not that big of a deal, but I have it in my table here. So here are the probabilities. You're going to win only 1/1000th of the time because there are 1,000 ways of picking 3 digits. That's 000 up through 999. If you made a list, there are 1,000 ways to do that. So there's a 1 out of 1,000 chance that you win. There's the rest of the time that you lose. And so we can take this and multiply through and then add things up. And so the expected value happens to be -50 cents. So this is typical of most state lottery games. And that is that people who play them will lose on average 50 cents for every dollar that they play. Which is horrible. It's horrible. It's like a tax on the stupid. So anyway, that is, let's see, I want to make sure I get this in order. Okay, well, oh well. I guess I have it in a different form over here. I don't know why I changed the way I did it, but I'll just, that's okay. I'll do it this way. Okay, so roulette. Roulette, on the other hand, now this is payout. So this is a little different way of looking at a gambling game. So you pay $1 to play this, and you get $2 if you win. This is if you bet on either black or red, and you get no money if you lose, and that's whatever the balance is, 0.5263, which the reason I've left this off the table off of my table is because when you multiply, it's not going to matter. But you'll have to trust me that this is the correct number. I mean, if you really want to see, I can show you what a roulette wheel looks like, and we can talk about why that probability is this way. But this is if you bet on either red or black, which is a common bet. But this is true of, I mean, what the answer that we get is going to be the same answer that you get for any bet on a roulette wheel. They've got the payouts sort of set up to rip you off the same amount, no matter how you bet. But anyway, here's the different bets. So remember, you're paying $1. So instead of back here, I was doing the expected value of the game, just from like looking at the whole game. This is the expected winnings. So expected winnings, and then we'll have to take into account the dollar that we paid. So the dollar that we paid has not been taken into account here. It's not that big of a deal. So anyway, you can see here that your expected winnings is going to be $2 times 0.4737 plus 0, of course, because if you lose, you get nothing. And so this ends up being 0.9 what's that, 9474? Yeah. So you can expect to win about 94 cents for every dollar you play. But remember, you're paying $1 to play. And so in reality, you come home with a nickel less, 5 cents or so. So what that means is you lose 0.0526. That's how much you lose for every dollar you play on roulette. So I guess that I shouldn't complain so much about how Ohio has legalized gambling, because the state takes, where is it? The state takes 50 cents for every dollar, rips off people that way. And then if you go to a casino, you only lose a nickel for every dollar you play. So they're much kinder to you than the state of Ohio is. Now, I mentioned that I do gamble. Well, not so much anymore, to be honest. But the gambling that I do is that I used to have a $500,000 life insurance policy on myself. No longer, because it was a term policy, and I feel like life insurance is important if you have people who are relying on your income. And I had 3 little people who were relying on my income. They're all gone now and making more money than I make. And so they don't need my income, so I don't have the life insurance. But back in the day, I had this $500,000 life insurance policy. Now I think I've got like 100,000, just enough to make my wife not so sad, I guess. I don't know. But getting back here, if you remember the probabilities, the probability of me dying, for example, that we looked at last time, it was about actually it was higher than this, wasn't it? Let's update. So that was what it used to be. It was more like this now, wasn't it? It's something really terrifying. But anyway, so when I say that I gamble, back in the day, I used to pay monthly for this life insurance policy. And if you think about it, what I'm paying for is I'm gambling and I'm betting that I'm going to die. Because if I die, then I get the big payoff, right? I get the $500,000. And if I live, I get nothing. So I actually would rather lose this bet. But so there's $500,000. You know what? I'm going to leave that what's there, because that's what it was back when I was actually carrying the policy. And so it's interesting to compare this with what I was paying for this policy. There, that's a little bit better. Okay, so let's see what my expected winnings are over the course of a year. So multiply this out, you get 500,000 times 0.002 plus 0. And I should have had this, well, actually I can do this, can't I? Let's see, 1, 2, 3. 1, 2, 3. I think I get 1,000. Is that right? So yeah. So I got $1,000. So my payout is 1,000. In other words, the life insurance company would have to charge me $1,000 a year to break even. Now they didn't, and the reason is that this was based on the CDC guidelines. The probability of me dying, because I don't smoke, I exercise, I eat reasonably well. They did this health, like I had to have like blood tests and all this other stuff. Anyway, my probability is probably a little, quite a bit less than that. At least back in the day, it's probably higher now. But anyway, I was actually paying $20 a month, which is only $240 a year. So actually a fourth of this. So they must have thought my chances of dying were about 1/4 of what this number is. But anyway, this is the sort of thing actuaries do. They try to figure out what is the expected value because they don't want to lose money on a bet. And they're betting that you're going to live, not that you're going to die. Okay, so I think that's it. That is it. Okay, great. So hope you have a great weekend. I'm going to stop the recording in case you have some special thing you want to chat about. Otherwise, I hope you have a great weekend. Get some rest. It's good for you. Let's see, Andy and Abby. Those are there. Good. Oh, stickers. Stickers are up here if anyone wants them. See you later today. Rachel, Austin. Not at. Karen, if you want to, Karen, you can stay in the front row. Yeah, but you're here before them. Wherever you're most comfortable.